Uh, Good afternoon, guys. Hope you guys are all doing well. Hope you've had a good weekend so far. I'm just gonna give a couple of seconds just so everybody's in. So there's just more people joining. But you guys are all okay? Can somebody drop me a message just so I know that you guys can hear me out? But I hope you guys are all doing well. Okay, more people are joining. Yep, good stuff. Good stuff. Wow, there's so many people this weekend. That's crazy. And you guys are just all looking at me. That's crazy. Hold on, let me just okay, there's more people. All right, cool, cool. So there's a few more people joining us. I'll just give a couple of seconds, but hope you guys are all doing well. As a quick intro for those of us that don't know me or this is your first time in the class today, my name is Daniel. I'm a GCSE and A-level maths tutor, and I've been running a couple of classes for you guys just to help you prepare for your exams. So we did a couple on pure, and then we did mechanics yesterday, and now we're going to do stats as we've got paper 3 on Tuesday. But yeah, so that is pretty much it. What I'm going to do now is I'm going to share my screen. Let me just check the chat just to see. Oh yeah, also as well, but I had to watch it live. I appreciate it as well. Guys as well, I've seen a lot of the comments on YouTube and stuff, and I'm very, very grateful. We uploaded the video for the mechanics one yesterday. It's already on 1,000 views, and that's down to you guys. So thank you so much. Really, really do appreciate it. So what we're going to do is we're going to do some questions. And since there's a lot of us today, just like last time, just like yesterday, you guys were very, very helpful in the chat. If there was any questions I missed, you guys were always helping each other out. So please continue to do that because it's quite hard for me to see all of the questions in the chat. But yeah, cool. So let's make a start. So I've got a couple of stats questions that I want us to try. And I'm going to try my best to keep it to an hour. Yeah, so I've got a couple of questions here. I'm going to try and do my best to get through everything in an hour. Yeah, so just going to let a few more people in. So we've got this one here. This is just a binomial distribution hypothesis testing. How do we find this as a question, guys? Having a look at it, we're going to start in a few seconds, but let me know. 0 if this is very difficult. Put a 10 if this is light work, not a problem. Okay, I can see 8s, I can see 5s, I can see 7s, I can see 6s. Okay, wagwan, wagwan. Okay, cool, cool, cool. All right, let's make a start then. So, yeah, what does it say? It says a dentist knows from past records that 10% of customers arrive late for their appointment. A new manager believes that there has been a change in the proportion of customers who arrive late for their appointment, right? And a random sample of 50 of the dentist customers is taken. Part A, for 1 mark, write down a null hypothesis corresponding to no change in the proportion of customers who arrive late, and an alternative hypothesis corresponding to a change corresponding to the manager's belief. Yeah, so more people are just joining, so I'm just letting them in. How many? 66. Wow, that's crazy. Anyways, so for part A, obviously this is a binomial distribution question because I labeled it, but obviously in the exam they won't tell you what are the key parts here. Well, we've got a sample size, n is 50. We've got 10% of customers arrive late, so that's a fixed probability of success, isn't it? Yeah, cool. So that will tell you that it's a binomial distribution. So let me put this here for part A. Now we need to write a null hypothesis. This is going to be H naught. And what does it say? Corresponding to no change in the proportion. Yeah, so we're going to say P is equal to 10%, which is 0.1. And then H1, the alternative hypothesis, is there has been, what was the manager's belief? There has been a change, right? So can somebody tell me in the chat, please? It's a hypothesis test. What type of tailed test is this? Is this 1-tailed or 2-tailed, guys? Exactly. Thank you very much. Thank you very much, Maddie, Terrell, Caitlin. Sorry, you guys are just too good. Yeah. So yeah, it's going to be not equal to because because we don't know which direction. Is it increased? Does it decrease? It's not specified. So it's going to be P is not equal to 0.1. Yeah, that's part A done. And then part B, so there's still more people joining. Let me just let them all in. It says, using a 5% level of significance, find the critical region for a 2-tailed test of the null hypothesis in A. You should state the probability of rejection in each tail, which should be less than 0.025. Yeah, so we've got our significance level to be 5%. So because it's a 2-tailed test, I write 2-tailed here. 2-tailed test, we have to half the probability, isn't it? Yeah, so 0.05 divided by 2 is equal to 0.025, isn't it? Yeah, so what we're looking for with this binomial model, right, is we're looking at 2 ends, right? We're looking for the first part where the probability of our critical value, so I'm just letting more people in, probability of our critical value would be less than, right, or equal to some critical value, right? This probability has to be less than 0.025. And then on the other side, we're looking for the other critical value where x is greater than or equal to some value of r, and this also has to be less than 0.025. Okay? So what we're going to do now is there's a couple ways to do this. What I always do, you can use your calculator, but it's always just good to just check the tables just to see if it will give it to you quite quickly, because remember the table gives it to you as less than or equal to, doesn't it? So what I'm going to do is I'm just going to get my table out. Just give me a sec. Okay, so let me share my screen. So I've got this here. Now this is the formula book that you'll get in the exam on Tuesday. Now this is for binomial cumulative distribution, right? And remember, what was our sample? Actually, let me go back to be fair, because I don't even think I actually labeled everything, did I? Hold on a second. Remember, the first thing that you do actually, which I forgot, you need to label your normal distribution, right? So NP, N is 50, P is 0.1. Yeah, that's the first thing that you need to do with a binomial distribution. So let me just go back there. So more people are joining, so I'm just letting them in. Okay. So now, if I go back to that table that I had here, right? So yeah, N equals 50 and P is equal to 0.1, isn't it? Yeah. So where are we looking? Okay. So yeah, let's look at this one here. So it must be this one, isn't it? Let me just, what I'm going to do, I'm going to just crop this and put this on the whiteboard. So I'm going to crop this because we're looking for 0.1. Yeah. So put this here. Go back to the whiteboard. So put this here. Yeah. Now remember what we're looking for. We're looking for the two critical regions on the lower side and on the upper side. Yeah. So we know that N is equal to 15 and P is equal to 0.1. So what we can see here is that, remember, we need the probability to be less than 0.025. Well, it's just this first one, isn't it? Because if I look at the second one here, this is more than that. This is more than 0.025. So on the lower side, right, the critical region for R will just be x is equal to 0, isn't it? So right, critical region, x is equal to 0. Yeah, because when I put in the probability of x equals 0, right, this gives me 0.0052. Make sense so far, guys? Yeah. Yeah, good stuff, good stuff. Yeah. Now continuing, now we need the upper end. Yeah. Now remember, if we're looking for a probability of greater than, when we're dealing with a binomial distribution, we have to do 1 minus, don't we? Yeah, because it's a discrete model. So what we're trying to do is, well, remember, we're looking for the probability that it's less than 0.025. So if I just scan quickly here, right? Well, looking at this here, I can see, well, if I do 1 minus these probabilities, it looks like it will be around here, isn't it? Yeah, these two values here for sure. Yeah. So what we'll do is, well, let's just say, for example, that one there, this one right here, this is the probability of x being less than or equal to 8, isn't it? Yeah. So probability of x being less than or equal to 8 is equal to that. Yeah. 9421. So what I want to do is, well, say, well, for example, because remember the second part is we're looking for a value of x which is greater than or equal to r. So if that's that there, then this will just be probability of x is greater than or equal to 9. This is equal to 1 minus the probability of x being less than or equal to 8. Yeah. And then putting this in here, let me just make this a bit better. This is an 8 here. Putting this in, let me get my calculator. This will give me 1 minus 0.9421. This is equal to 0.0579. This is too big, isn't it? Yeah. 0.579. This is bigger than 0.025. Yeah. So we're going to go up one. Yeah. To this one here. Now this one here is the probability of x being less than or equal to 9, isn't it? And this is 0.9755. So therefore, we can say, well, that means that the probability of x being greater than or equal to 10 is equal to 1 minus that probability of x being less than or equal to 9. So we're going to plug this in then. And then what does this give us? We put it in 1 minus, what is it? 0.9755. This is equal to 0.0245. So this is just below. Yeah. This is less than 0.025. So this is perfect. Yeah. So therefore, our answer for part B, critical regions, right, will equal x is equal to 0 on the lower side, right? And x is greater than or equal to 10 on the upper side. And that is our final answer. Does that make sense, guys? Let me just zoom out a bit just to see. I'm just going to check the chat as well. Yeah. So can you always look at the table? Yeah, you can always look at the table. Just sometimes it just depends on what is quicker. Yeah. So because we're looking for the lower part anyway, less than or equal to, I would look at the table just to see if you can get it straight away. Luckily, this question did. Yeah. Sometimes when you're doing it with the calculator, it's a bit more guesswork. Does that make sense? But you can do it with the table. Yeah. How did I know it was binomial? Because to be fair, I shouldn't have labeled it. But anyways, it says, Edexcel knows from past records that 10% of customers arrive late for their appointment, right? A new manager believes that there has been a change of proportion of customers. A random sample of 50 of the dentist customers is taken. Yeah, so there's a fixed, remember the characteristics of a binomial distribution. There's a fixed sample size, n equals 50. There is a fixed probability of success or failure. 10% of customers arrive late. That means p is equal to 0.1. Yeah, does that make sense? Oh, thank you very much. Thank you very much. Thank you very much. I just saw a message. Yeah, this is normal distribution, right? I put an N here. Thank you very much for that. I just saw it in the chat. Yeah, this should be B. X is binomially distributed. Thank you very much, guys. Really do appreciate it. You know? So if for the X equals 0, the answer is greater than 0.025. So we reject it. So for X equals 0, answer is greater than 0.025. So for X equals 0, the answer was less than. For X equals 0, it was 0.0052, right? So that was less than 0.025. So we take that as our critical value. Understand? Okay. So let me just see here. Okay, so what we're gonna do, I've got a couple of questions. I'm gonna go through them as best as I can. But if you're seeing them in the chat, please help me out as well. Yeah. So we've done part B, and then part C says, find the actual level of significance of the test based on your critical region from part B. Can somebody tell me what we do here? How do we find actual level of significance? Exactly, exactly. You just add the probabilities that you found in your critical regions. Thank you very much, Churo, Abel, Janice, good stuff. Yeah. So all we're going to do is for actual level of significance, it's just going to be the probability of this one here, 0.02, 0.0052 plus, and then this one here, which was here, right? 0.0245. That's all you do when they ask you for an actual level of service. Always a one marker. You just add the probabilities that you got for your critical values. Does that make sense? You know? So let me put this into my calculator, see what I get. So 0.0052 plus 0.0245. This is equal to 0.0297. Just double check that. Yep, perfect. Now part D, it says the manager observes that 15 of the 50 customers arrive late for their appointment. With reference to part B, comment on the manager's belief. So what do we do with this one, guys? What do we do with this one? The manager observes 15, yeah? And we're comparing it exactly. Thank you very much. Compare the critical value to 15. Thank you very much, Denise. Yeah. So all you're doing now is looking. Well, remember, what was the critical region in part B? It was X is equal to 0 on one side, right? And it was X is greater than or equal to 10 on the other side. Now that observed value, right? That observed value is just X is equal to 15. Yeah. This lies within the critical region. Yeah. Lies inside critical region. Yeah. So what does that mean, guys? If it lies inside the critical region, what does that mean? Exactly. Yeah. Thank you very much. We reject H0. Yeah. It's statistically significant. Yeah. So we reject H0. So I remember when you're doing these questions, you always have to contextualize it. Yeah. So let me just put this out. So you'd say, since, let me make this a bit big as well. A bit bigger. Okay. Since X equals 15 lies inside critical region, yeah, there is evidence to support the manager's claim. To support, what was the claim again? A new manager believes that there has been a change, yeah? So all I would do is say just, there's evidence to support that there has been a change, in the proportion of customers arriving late. Customers arriving late. No? And obviously what we're doing here is that we rejected H0, accepted H1. Make sense, guys? Anybody got any questions on that just before we continue? Yeah, how is it within the critical region? Because remember, the critical region was x equals 0 for one side and x is greater than or equal to 10 for the other side. The observed value is x equals 15. That is more than 10, so it lies within. Does that make sense? Yeah? Okay, okay, cool. So what I'm going to do, let me just see here, what was, so just quickly, just as a brief overall recap of part B, it says use a 5% level of significance to find a critical region for a two-tailed test, right? So remember what you're doing when you're dealing with a two-tailed test is obviously we half the significance level. So obviously it's going to be 0.025 that you're looking for, right, on each side. So what you're doing is you're calculating the probability using a binomial model of you getting a value of less than 0.025. And on the lower end, we could see from the tables that it was just 0.052. Yeah, 0.0052. Yeah. And then when we looked at the upper end, we had to do 1 minus. So we just gauged it a bit. We looked at 8, we looked at 9. We did 1 minus each one. And then the first one that gave us a value which is less than 0.025 was x being greater than or equal to 10. So that way, the critical region or the critical values was x equals 0 on the lower side, x is greater than or equal to 10 on the upper side. Yeah. Hope that all makes sense. And I really appreciate, I can see a lot of you guys helping out in the answers in the chat as well. So I really appreciate that. So what we're going to do now, let me admit everybody, there's still more people joining. So we've done that one. Let's go to this one here. Now, Venn diagrams. We know that this is always going to come up. How do we find Venn diagrams as a question, guys? Put a 0 if you're thinking, I can't wait for the Venn diagrams questions to come up. And put a 10 if this is absolutely light work. This is super, super easy. Yeah, I can see 10, 9, 5s, -9, light work, 7s. Okay, so on average, it depends. Okay, fair enough, cool. Let's look at this one. Now, what does it say? It says a large, let me look here. A large college produces 3 magazines. One magazine is about green issues, one is about equality, and one is about sports. A student at the college is selected at random, and the events G, E, and S are defined as follows. G is the event that the student reads the magazine about green issues. E is the event that the student reads the magazine about equality. S is the event. So let me just, people out, let me just delete that long gang. Let me just, hold on, let me just do that, annotate, 1 second. Okay, I think that should be fine. Okay, cool. All right, so let's continue. All right, I think that should be okay now. But yeah, cool. Anyways, let's continue. So it says the Venn diagrams. So the Venn diagrams where P, Q, R, and T are probabilities gives a probability for each subset, right? And then for part A, it says find the proportion of students in the college who read exactly one of these magazines, right? So let's get the diagram here. So this one is the diagram, right? So got this here. The proportion of students who in the college who read exactly one of these magazines are just going to be these parts here, aren't they? This part here, right? One of these magazines here, and this part here, right? And this part, yeah? Because these are the parts of the Venn diagram where only one magazine is read, isn't it? Yeah? So all we're going to do for part A is just add these together, aren't we? Yeah? Part A. So put this here. We get this. Put in this here. So this will be 0.08 plus 0.09 plus 0.36. Yeah, this is equal to 0.53. Yeah, So 0.53, just adding these three together. Now, for part B, it says no students read all three magazines, and the probability of G is equal to 0.25. And with this information, we need to find the values of P and Q. Yeah, so let's do this. We got this here. Put this here. Okay. So got this, and we know that no students reads all three magazines. So what does that tell me if no students read all three magazines, guys? Exactly. Thank you very much. P equals 0. Yeah, P equals 0. Because the intersection of all three is 0. So from that one, we can say for sure P is equal to 0 there. And then we know that the probability of G is 0.25. Well, the probability of G, right, is this one in the top left-hand corner. We've got this here. And then if this entire thing is 0.25, right, then all of these values together must add to make that. Now, obviously, we know that P is equal to 0. So all we're going to do to figure out what Q is, well, Q will just be equal to 0.25 minus the 0.08. Yeah. And then we're going to minus the 0.05, aren't we? Yeah. And obviously, P is 0. So we're just going to leave it at that. Yeah. So let me just put this in the calculator. 0.25 minus 0.08 minus 0.05. This is equal to 0.12. Yeah. So Q is equal to 0.12. Okay, so that's fine. That's part B done. Now, what does it say for part C? Part C says, given that the probability of S happening, given that E happens, is 5/12, we need to find the value of R and the value of T. Yeah. All right. Now, this is just a conditional probability. Yeah. Now, how many of us remember our formula for conditional probability? The probability of A given B happens, right? This is equal to the probability of the intersection of A and B divided by, can somebody tell me in the chat? Exactly. Thank you very much. The probability of B. Yeah. Fantastic. Good stuff. Yeah. And just to make sure you understand that, right? Just quickly, if I draw two Venn diagrams like this, right? And I'll draw another one like this, you get another circle like this here. Like that, right? And let's say this is A and this is B. This is B here. And I'm looking for the probability that A happens, given that B happens. Well, for sure, I would need to be in the circle of B, the probability space for B in its entirety, right? And then obviously, if I'm looking for the probability that A happens, given that B happens, well, I have to look at the part of A which is included in B, right? So let me just get a different color here. This won't even work, to be honest. But yeah, so it's that fraction, isn't it? Yeah, so this part is meant to be orange because the highlight is not working. But yeah, you guys get the idea. Yeah, so for sure, the probability of A given that B happens is the intersection of A and B divided by the probability of B. Yeah, so now we're just going to use that here. Now, looking at the Venn diagram again, let me get this here. Let me copy this again. Okay, so this is our Venn diagram, and we're looking for the probability of S given that E happens. Well, we're just going to do the exact same thing, aren't we? Yeah, we're going to say the probability of S given that E happens is just equal to the probability of S intersection E divided by the probability of E, isn't it? Yeah. Okay. Now looking at the diagram, where is S intersection E? Well, it's just this part here, isn't it? This part here is S intersection E. Now remember, P was equal to 0 from part A. So for sure, the probability of S intersection E is just R, right? Because remember, it's P plus R, but P is 0. We found that out in part A, yeah, or part B, whatever part. Yeah, so we'll put R here. And then now, what is the probability of E happening? Well, it's just this entire circle for E, right? So we're going to say, well, we've got 0.05 plus 0.09. That's just 0.14, right? And then we've got P plus R again. Again, P is 0, so it's just R. So we've got this here. Yeah? Does this make sense, guys? I'm going to give a couple of seconds. This part is very important when you're doing this question. Is this all okay? Yeah? Good stuff. All right, cool. Good stuff. All right. Now remember, this from the question is equal to 5/12. Yeah? So I'm going to make this equal to 5/12 here, and then I get an equation in terms of R that I can now solve quite easily. Yeah? So let's just solve this very quickly. So we're going to cross multiply. we're going to get 12R is equal to 5 lots of R plus 0.14. And then now we can just expand, can't we? So what's that? That's 0.7, isn't it? Let me just double check. 5 times 0.14. 0.14. Yeah, I thought so. Cool. So 12R is equal to 5R plus 0.7. Yeah. So that tells me that we move this over. So that means that 7R is equal to 0.7. Yeah. So therefore, we just divide by 7. This is going to be equal to 0.1. Yeah. So we now know the value of R, which is 0.1. Now we needed to find the value of T as well. Now we know all of the values. We know Q, P, R, right? Now to get T is just going to be equal to 1 minus everything, isn't it? Yeah. So I've got this here. T is equal to 1 minus, and then I'm going to subtract every single thing I see here. So I'm going to do 0.08 minus 0.05 minus 0.09 minus Q. Q is 0.12 from before. P is 0, so I'm not going to put anything there. We've just calculated R to be 0.1, and this one here is 0.36. Yeah. All we're going to do is just put this into the calculator and see what it gives us. We just do this very quickly. Got this here. So it's going to be 1 minus 0.08 minus 0.05 minus 0.09. Making sure it's all correct, that's fine. Minus 0.12 minus 0.1 minus 0.36 1/5 0.2. Yeah, T is 0.2. Make sense, guys? All okay with this? Yeah, good stuff. And I can see you guys discussing about questions and stuff in the chat. That's good. Yeah, cool. Good stuff. All right. I see Maths in the chat as well. That's a really good website, to be fair, for good for harder questions as well. But yeah, so that one's done. Now we've got this last one here, right? Got this last one here. Now, this one here, how much room have I got for this one? Oh, let me see. I'll do it here, to be fair. One sec. Let me just zoom in. All right. So we've got this here. All right. Now, it says determine whether or not the events S intersection, not E, and G are independent. Show you're working clearly. So can somebody remind me, please, what is the formula for independence? Thanks for allowing me to borrow your Lambo. Yeah, thank you very much, Alex. Exactly. Yeah, good stuff. So the formula for independence is probability of A intersection B is just equal to the product of these two probabilities individually. Yeah. So what you want to do in a case like this then as well, we just need to actually work all of these out. Yeah. So S not E is equal to the probability of what have we got here? Determine whether or not these are independent. So yeah, to be fair, we've got to put this here, don't we? Yeah. So I'll do it like this here. This here, and then G, right? If they're independent, then this will follow. Times the probability of G. Yeah. So what it is for this one, it's our job to calculate both of these probabilities and see if they're equal. If they are, then they are independent. If they're not, then they're not independent. Simple. Yeah. So let's have a look then and see what we've got here. So what do we want to work out? So let me get the Venn diagram again. I'll do it one more time. Okay. So we need to work out these probabilities here. Now, from before, let me just check the question. The probability of G is equal to 0.25. Yeah, so let me put that there because we're going to need that anyway. Yeah. Probability of G is equal to 0.25. Oh, it's doing this glitching thing again. So one second, guys, I'm gonna close it. Let me just go to the, okay, let me put this in. I'm just gonna close this quickly and then open it again because it's doing this glitching thing. Okay, I think that should be okay now. Okay, so continuing, right? Okay, so what do we have? Well, we've got the probability of G. Remember, we know that's equal to 0.25, as I was saying from the question. Now we need to work out the probability of S not intersection E. right? So probability of S intersection not E. Yeah. So the way I like to do these ones is I always just like to you can do it quite simply, but I always like to draw a diagram just to see what actual parts I'm looking for. Yeah. So for example, if I want to figure out probability of probability of S and then not E, what I would do is, well, what is the probability of S? Probability of S, right, is this part. Where's S? This part here. Yeah, this part here. And then now I would work out the probability of not E. And that's just everything on the outside of E, isn't it? Yeah. So put this here. So just be like this. Yeah. This is not E. So then to work out the probability of the intersection of these two would be the parts where the shaded parts overlap, right? And we can see clearly, right? Where do these two shaded regions overlap each other? Well, it's just only for this part here, isn't it? This part here, right? This part here. Yeah, these are the only two places where they overlap each other, the shaded regions. So the intersection of both of these two would be equal to, I'll put this here, probability of S intersection not E would be equal to Q plus 0.36. Are we all okay with that, guys? Yeah, good stuff. All right, now remember, from part A or B, Q was equal to 0.12. Yeah, so therefore, this is just going to be equal to 0.12 plus 0.36. This is equal to 0.48. Okay? So we now know the probability of S intersection not E. Yeah, it's 0.48. Now remember what we're trying to do. We're trying to test whether these two events are independent, right? So let's work out one part of it. Well, we've got this part on the right-hand side. We can now calculate. Yeah, I'm going to copy this here. Well, we know what these are both equal to, right? This is 0.48 here. Times by this is 0.12. Yeah. So all we're going to do here, sorry, that's not 0.12. That's probability of G. Sorry, where's probability of G again? That was 0.25, I believe, wasn't it? It was somewhere. Yeah. Probability of G was 0.25. Yeah. So therefore, this one here, probability of G, which is 0.25. This will just be a quarter of that, isn't it? So this will just be 0.12 here. Yeah. So therefore, this answer here, the probability of the two events times together is 0.12. Now we need to see whether or not the actual intersection of both of them are the same. If they are, if it's also equal to 0.12, then they're independent. Yeah. So we've done one part of it. So we've done this part. We've done the right-hand side. Tick. We'll tick this part here. This part we've ticked, right? This is 0.12. And let's work out what this is. Yeah. Copy here. Okay. Doing this here. Now we've got this, right? Now, what are we looking for? We're looking for the intersection of these two events. Well, what was the event of S intersection of E? It was just Q plus 0.36, isn't it? So if I get these two Venn diagrams together one more time, right? Well, this one here is a S intersection, not E. Now remember, that was just this part for sure. That was just this part here, right? That was just this part here. And then obviously the probability of G here is this entire thing here, isn't it? Now you ask yourself again, so this is the probability of G, probability of that. Now you ask yourself again, remember, we're looking for the intersection of those. So again, where do these two shaded regions overlap each other? The only part where they overlap each other is for Q, for sure, right? So we can say the probability of S intersection not E, right? And the intersection, right, of G for sure is just Q. But remember, Q from the question was 0.12. So can you see now we've proved it? We've tested independence and both of the probabilities, right? They both equal 0.12. So what you can say just to finalize it, you can say that, well, therefore, the probability of S intersection not E, right? Like this and G, this was equal to 0.12. And the probability of S intersection E multiplied by the probability of G was also equal to 0.12. So therefore, they are independent. Perfect. Done. Make sense, guys? You all okay with this? Yeah, good stuff. Good stuff. Good stuff. We're happy if this comes up in the exam, yeah? All right. Now let's continue. Let's continue. We're going to do this one here. Yeah? Okay. So we've got this here. Now, probability distributions. What are we thinking about a question like this, guys, if this comes up on Tuesday? Put a 0 if you're looking at this, just scanning it, thinking, don't know what's going on here. We're very confused. And put a 10 if this is just super, super easy. Peak 0, 18, meh. Okay, okay, okay. So yeah, let's have a look at this one and see how we get on. Yeah, I've done this question a couple of times with my students as well, to be fair. So let's see. So you got this one here. Now the first part says, in an experiment, a group of children repeatedly throw a dart at a target. Yeah. For each child, the random variable h represents the number of times the dart hits the target in the first 10 throws. Peter models h as being binomially distributed, right? With 10 and 0.1. Yeah. So remember, what we've got here basically is we've got h is binomially distributed. I remember this time, 10 and 0.1. Yeah. Now, part A says, right, state two assumptions Peta needs to make to use her model. What do we do with this one? Exactly. Thank you very much, Joshua. The probability remains the same and the events are independent. Yeah. Success or failure, fixed events, independent, fixed number of outcomes. Exactly. So what you're doing with this one is you're just really remembering your characteristics of a binomial distribution. So let me just get this up quickly. I've got something that I got from the actual book. Just give me a second. I'm just going to try and find it. Where did I put it? I think I did it here. Yeah, perfect. 1 second. You'll see it in a second. I'm just on another page. I'm just getting it here. Yeah. So basically, what you do with these types of questions here, right, is you're just remembering this. Yeah. How many of us remember all of these? 10 out of 10. Yeah. Cool. Cool. So all you're doing, okay, you can see zeros, nines. No, okay, well, just remember, you need to remember this for the exam on Tuesday because they can ask you this as well. Yeah, they can say at the end of a question, state why you've chosen a binomial model or why is a binomial model appropriate. You need to remember these 4 characteristics here. Yeah. So in the context of the question, in an experiment, a group of children each repeatedly throw a target. For each child on a variable is the number of times. So what you could say, and they only chose 2 in the mark scheme, from what I remember in the mark scheme. I think the other one was the probability of hitting a dart. So just contextualize it. The prob of hitting the target remains the same, remains constant, yeah. And the other one was each throw is independent. Yeah, that's what they put in the mark scheme. But what I would just recommend, right, is just memorizing all of these bullet points, yeah, from one another. Perfect. Yeah. All right. So we've done part A. And then part B says, well, using Petter's model, find the probability of H being greater than or equal to 4. Well, this is easy. This is a binomial model. It's going to be 1 minus the probability of H being less than or equal to 3, isn't it? Yeah. So all we're going to do now is we're just going to put this into our calculator, aren't we? Yeah. So let's do this. Let me get this up here, and then it's 7, isn't it? And it's binomial CD because we're testing for cumulative probability. 2 here. What's our contact plus on? Apologies. 7. Where's binomial CD? Oh, it's 1. That's why. Yeah. 2. Okay. So what is what we're looking for? Remember, the calculator gives it to you as less than or equal to. So I'm gonna put 3 here. N was how many throws? There were 10 throws, and the probability is 0.1. Yeah. 0.1. So therefore, we get this here. This is the probability of it being less than or equal to 3. So we're just going to do 1 minus that, aren't we? Yeah? So what we're going to do now is this actually stores in your calculator. So all I'm going to do is go back to the normal one and do 1 minus answer. This will give me this here. Yeah? Just make sure you guys can see that. So that one there, I'll just screenshot it. Whoops, a second. Get this here. That all clear, guys? Gonna make sure we're all okay with that. Yeah? You guys are just having a chat. That's good. Just discuss. Yeah, good stuff. All right. Cool. Cool. So you've done that one. That one is fine. Now, sorry, my thing is glitching in a sec. 1 second. Yeah, perfect. All right. Now, obviously, it hasn't given us to round to any significant figures. So what do? You round to 3 significant figures, don't you? Yeah. So the answer with this one will be 0.0128 within it. Yeah. All right. Cool. Now, part C. What we're on part B, part A, part B, part C. All right. Now it says for each child, the random variable f represents the number of the throw on which the dart first hits the target. Using Petter's assumption about this experiment, find the probability of f equaling 5. Yeah, so let me put this here. Get this here. This is part C. Yeah. Now, what was Petter's assumption? Petter's assumption is that when you the probability of you hitting the target is 0.1. Right? That was Petter's assumption. Remember, she modeled this a whole scenario in the binomial model, didn't she? Yeah. The probability of you hitting the target was 0.1. So I'm just going to check the chat quickly because I can see I'm sure a lot of you have already got the answer. Probably hitting is going to be equal to 0.1. Yeah. Let me see what everyone's put in the chat. Okay. Yeah. Okay. So let's read it again. For each child, the random variable f represents the number of the throw on which the dart first hits the target. And we need to find f equaling 5. So what does that mean? That means that we threw the dart 5 times, and on the 5th occasion we hit the target. We need to calculate the probability. Well, if f equals 5, that represents that tells us it took us 5 throws. What does that imply about the first 4 throws, guys? Exactly. We must have missed it. The first 4 goes, and then we hit it. Well, the probability of hitting it is 0.1. The probability of missing it, right? Because remember, this is a binomial model. It's constant. This must be 0.9. So, for example, the probability of f equaling 5, right? This must be equal to missing 4 times, right? And hitting it once. Hits once, yeah, on the 5th go. Well, missing 4 times, well, the probability of us missing it once would be 0.9. Can somebody tell me what I need to do with that 0.9, please? Exactly. We need to raise it to the power of 4. Be very careful. It's not timesing by 4. It's to the power of 4. Because remember, it's basically you miss it once and you miss it again and you miss it another time and you miss it for a 4th time. Remember, and means multiply, doesn't it? So we need to multiply this by itself 4 times. That's just to the power of 4. And then we're going to times by hitting it once because we hit it on our 5th occasion. So it must be 0.1 here. Yeah. So therefore, putting this into the calculator, this will give us 0.4 to the 0.9, sorry, 0.9 to the power of 4 multiplied by 0.1. This is equal to 0.0656 to 3 significant figures, isn't it? Let me just double check that. 656. Perfect. Makes sense, guys? We all okay with this? Yeah, good stuff? Good stuff. All right, now let's continue. So we've done that. Now let's see what we've got next. Okay. So we've got this here, right? Now part D says, Thomas assumes, actually, let me read it first. Thomas assumes that in this experiment, no child will need more than 10 throws for the dart to hit the target for the first time. He models the probability of f equaling n, right, as the probability of f equaling n is equal to 0.01 plus n minus 1 times alpha, where alpha is a constant. And the question asks us to find the value of alpha. Yeah. So with this one, put this in here. Let me screenshot this quickly and put this here. Yeah. So, all right. So this one here, well, let's read it again. Thomas assumes that in this experiment, no child will need more than 10 throws for the dart to the target. The probability of F equaling N, well, what does N represent? What the number of throws, right? This is given by this equation here. And we need to find the value of alpha. So what are our thoughts on this one, guys? How do we go about doing this one? Heart failure, Oli Benson. You guys are hilarious. You guys are just having a chat. Okay, so this one here, guys, right? Now, this is a different, we need to be careful here because remember, we've got, remember with these questions, right? Part A, we had Peta. She had a model for throwing this target, right? It was constant, yeah? The probability of you hitting the target with the dart, right? Now, Thomas assumes that in this experiment, no child will need more than 10 throws, all right? So the maximum amount of throws is 10. And we're looking at the probability of you hitting the target, right? It could be 1 throw, it could be 2 throws, 3 throws, or four throws, and so on and so forth. So do we agree, just by this formula here, the probability of you hitting the target is no longer constant? Do we agree with that? I want us to say yes or no, because that's very important. Yeah? Yeah? It's no longer constant, right? So we're not using a binomial model anymore. That's the first thing, right? This is just a probability distribution now, right? So what I'm going to do is let me just get something just so it makes more sense. Okay, wait, why? Because remember, this here is the definition of you hitting, the probability of you hitting the target. It's 0.01 plus the number of throws minus 1 times some alpha. That is going to change, right? N is variable. N goes from 1 to 10. So the probability of you hitting the target is going to vary. It's not constant, just due to this formula. Does that make sense? If I plugged in a value for N, the number of throws, it's going to be different if I plugged in 10 or 5 or 2. Does that make sense? Yeah? All right, cool. So what I'm going to do, I'm just going to get something very, very quickly. Let me just get this very, very quickly. Where is it? What I'm looking for? This thing right here. Okay. Okay. So I've got this table that I found in the book. Table isn't really great. I mean, the screenshot isn't really great, but I'm just going to show you here. Yeah. So what you're doing basically is this, right? I've got this table. I've got this from the Edexcel book. I'll see if I can find the actual one, which is a bit better, right? So remember, when you this here was the probability of you throwing a dice, right? We know that it goes from 1 to 6 because there's 6 faces, and it's each 1 6 1 6 1 6, right? Now, what we're going to do here, we're going to model this the same way. Obviously, it's not constant this time, but it's the same type of principle whereby with the one on the right, there were 6 different faces. On this one, nobody needs more than 10 throws. So what we're going to do is we're going to draw a table like this. Yeah. This here. Like this here. Yeah. And I'm going to say, well, we've got N here, right? And we've got a probability of F equaling N here. Yeah. Now, if I just put lines like this here, we do it bigger. Right. Now, for example, remember, Thomas assumes that in this experiment, no child will need more than 10 throws. So you could do it in 1 throw. You can do it in 2 throws, 3 throws. Or you can do it from 9 and then 10. Yeah, I'm going to put dot, dot to be fair. Let me do this. Put this here. Like this here. And I'll put dot, dot, dot. Yeah. So it goes from 1 to 10. Now, what you want to do with a question like this, guys, is you want to just try and understand it. Try and plug things in and see what happens. Well, for example, we've got this probability distribution here, right? Got this here. Paste this here. Now, what does it say? Well, remember, N is the number of throws. So for example, if N was equal to 1, for example, it would be 0.01 plus 1 minus 1 alpha. That is 0 times alpha. This is just 0.01 then, isn't it? Yeah. So the probability of you hitting it on your first go is 0.01, right? Now, what about on the second go? We're just going to change N to 2. Well, what would that be? That will be 2 minus 1 here, if it's N equals 2, right? And that will just be 1 alpha. So this one will be 0.01 plus 1 alpha. And then obviously, just following that process, this has to be 0.01 plus 2 alpha, and so on and so forth. What I'm going to do, actually, let me do this here just so there's room. Yeah. This one here is 0.01 plus 2 alpha. And can you see what's going on here? When I'm on my second throw, it was 1 lot of alpha. When I'm on my third throw, it's 2 lots of alpha. So when I'm on my 9th row, guys, when I'm on my 9th row, how many lots of alpha will I be putting into my expression? Exactly. It'll be 8 lots. Yeah. So it's always a pattern going on with these types of questions. And then obviously this one will just be 0.01, right? Plus 9 alpha. Okay. So now they've asked us to find the value of alpha. Now we know when they ask us to find the value of some variable or some constant, in this case, it's a constant, right? We need to solve an equation. So we need to somehow construct some sort of equation here. Anybody have any ideas as to how we go about that? Exactly. Thank you very much. In a probability distribution, all the probabilities must sum to 1. So then we can say, well, if that's the case, well, then all of these probabilities here, they must sum to 1. So I'm going to say 0.01 here, plus the next one, 0.01 plus alpha, plus 0.01 plus 2 alpha, right? Plus all the way up until the 10th row, this is going to be 0.01 plus 9 alpha, isn't it? And we know that this is all equal to 1. Now, we've got an equation in terms of alpha. Now, why have I done it from why have I done 2 alpha and then I put dot, dot, dot all the way to 9 alpha? The question is not, they're not expecting us to actually manually get every single expression and then solve it. What is this looking like, guys? Exactly. Thank you very much, guys. This is just an arithmetic series, right? Why is it an arithmetic series? Because we can see we've got a term here. This is the first term. And then every other term, I'm going to put this in a red bracket, right? I'm going to put these in a red bracket. Every other term differs by the same amount, doesn't it? We add on the value of alpha each time. So for sure, 110%, this is an arithmetic series. So what is our first term? A is equal to 0.01, right? Our constant difference, our common difference is alpha, right? Let me put this here. D is alpha. And remember, how many throws were there? Well, it goes from 1 to 10. N is equal to 10. Yeah? Does that make sense, guys? Let me write arithmetic. Arithmetic. Can't spell it today. Series. Yeah, we all okay with that? Okay. Good stuff. Now, we're looking for the sum to n terms. What is the formula for the sum to n terms? Well, remember, it's Sn is equal to n over 2, right? 2a plus n minus 1d, isn't it? Yeah? Okay. So what we're going to do then is we're just going to apply this formula with the values of a, d, and n and make it equal to 1 and then solve, right? So let's do this here. Well, it's S10 because there's 10 throws. So it's be 10 over 2 and it will be 2 lots of alpha, right? So I can just write 2 alpha to be fair. Sorry, 0.01, sorry, because a is 0.01. I'm getting confused with the a and the alpha now. And then plus n. Well, what is n? N is 10. 10 minus 1 is 9. So this will be 9. And then d, our constant difference is alpha. Yeah? And we know that this is equal to 1. Yeah? So all we're going to do now is just tidy this up and then solve it. And that will give us the value of alpha, wouldn't it? Yeah? So let's do this. We're going to have 10 over 2 is 5. And then we're going to have 2 times 0.01 is 0.02 plus 9 alpha is equal to 1. Now this is easy. Expanding the brackets, this will give me 0.1 here. This will give me 9 times 5 is 45. 45 alpha is equal to 1. So therefore, we can say 45 alpha is equal to 0.9. And then that is just going to be equal to that, isn't it? 0.9 divided by 45. Yeah? So I'm going to put this into my calculator, see what it gives me. 0.9 divided by 45. This is equal to 0.02. So alpha is 0.02. Does that make sense, guys? We all okay with this? Yeah? Good stuff. All right. Now, continuing. We've done that. Now, what does the next part say? I think there was just 2 1 markers. So, got this here. Let's do these 2 now. We now know what alpha is, 0.02. Now the question says for part E, using Thomas's model, find the probability that f is equal to 5. Well, what was Thomas's model? Thomas's model was this equation right here. Yeah? So this is perfect now because we now know what alpha is equal to. We can just plug in 5, can't we? Yeah. So let's do this here. Well, if I want f is equal to 5, right? Probability of f equaling 5, right, will equal 0.01 plus n minus 1. N is 5, so this would be 4, right? And then alpha. Alpha, we know, is 0.02. Yeah? 0.02. So we're just going to plug this in, aren't we? Plug this in. 0.01 plus 4 lots of 0.02. And this is equal to 0.09. Perfect. Now, that one's done. Part F says, now, for 1 mark, explain how Pater's and Thomas's model differ in describing the probability that a dart hits the target in this experiment. How do we do this one, guys? What is this? What is this one for 1 mark? Exactly. Right. Thank you very much, Renee. So remember, with Thomas's model, the one that we just did, right? The probability of you throwing, of you hitting the target, right, is changing each time. It's 0.01 plus, is 0.01 if you do it once, it's 0.01 plus alpha if you throw it for a second time, it's 0.01 plus 2 alpha for a third time, and so on and so forth. The probability of you hitting the dart is changing the more throws you get. Now remember, with Petter's model, originally, it was a binomial model. The probability of hitting the target was constant, right? So all you would need to say for part D, right, is this. I'm going to type it because my handwriting is atrocious, right? For Thomas's model, the probability of hitting the target changes, or it increases, yeah? Because it actually does increase. The more throws you have. Whereas with Petter's model, it remains constant. That's it. Does that make sense, guys? All okay with this? Yeah, so the probability increases. Yeah, yeah, good stuff. And I just saw, is this a difficult question, or is it just for you? But it makes sense. Yeah, I mean, this is an exam. If you get this in an exam, you're chilling. All you need to know is you just need to understand your probability models well, right? If you get this, can come up in your exam. It came up for 2018. This is from the 2018 paper. So yeah, if they saw this, hopefully they were chilling and they found it easy. Yeah. Okay. Yes, but why with Thomas's model is the sum to n terms equal to 1? Because remember, just very quickly, remember, this is a probability distribution, right? Now, we're going from 1 to 10. The probability if you hit in the first row, 0.01, second row, 0.01 plus alpha. All of these probabilities in any probability distribution has to sum to 1. Probabilities always add to 1. So that is why the sum to n terms, because this was actually an arithmetic series, right? We made it equal to 1. Does that make sense? Then what topics are you predicted to come up? To be honest, right, I'm just a tutor, so I haven't got the inside scoop. But from what I have seen in past papers, I would just say just practice normal distribution, hypothesis testing. Maybe what came up last time, I can't even remember. But just the main things, binomial distribution, Venn diagrams for sure will always come up. And maybe just based on what's come up in 2022 and 2021 as well. Yeah. But I hope that answers your question. I'll see if I can find a couple of predicted papers. But yeah, sorry guys, again, it is 1 o'clock. We're going to do one more, right? Now, if you need to go, completely understandable. Apologies for overrunning. Sometimes it just takes a bit of time. And yeah, so we're going to do this one here. This is a normal distribution question, right? I should really stop saying that because you should be able to, I should tell you to like guess, but yeah. But looking at this one, guys, how do we find this one? How do we find normal distribution? Dan, if you see Alex, you're hilarious. Yeah, fun, easy, good stuff. 6.5, I don't even know. Okay, so I've just got a question that pretty much encapsulates all of normal distribution, right? Well, I'll try my best to. So let's have a go at this one for the last one and see how we get on with it. Yeah. So Let's read what it says. It says the lifetime L hours of a battery has a normal distribution with a mean 18 hours and a standard deviation of 4. So first thing first, always write out your distribution. It's defined as L, the lifetime. This is normally distributed with mu. Remember, mu is the mean, 18, and the standard deviation is 4. So sigma squared, isn't it? So 4 squared, right? This is how we always model it. Yeah. All right. Now it says Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. Part A says find the probability that a randomly selected battery will last longer than 16 hours. Okay, well, this is just a normal distribution. So all we're looking for here for part A, right, is the probability of L being greater than 16. Yeah. So what you could do as well, actually, before you start these questions as well, just always visualize it too. Yeah. Just always draw your normal distribution bell curve and just say, okay, well, I've got this here, right? This is so bad, but the mean is 18 and so on and so forth. Standard deviation is 4. Anyways, cool. So what we're going to do now is just going to get our calculator, put this in. 7, we're going to go to a normal CD, aren't we? And then the lower bound, right? Because we're looking for greater than 16 will be 16. And then what I always do, I just put a really big number for the upper bound because it's just more than, yeah? So I always just do 10 to the power of 10, yeah? So not 10 squared, 10 to the power of 10. The standard deviation is 4. The mean is 18, yeah? So putting this in, we get this number here, yeah? Now, obviously, to 3 significant figures, this would just be 0.691, wouldn't it? 0.691 for 1 mark. That's not too bad. Now, for 5 marks, it says, at the start of her exams, Alice put 4 new batteries in her calculator. She has used her calculator for 16 hours, but has another 4 hours of exams to sit. Find the probability that her calculator will not stop working for Alice's remaining exam. So looking at this one for part B, guys, what are our thoughts on it? Put a 0 if you look at this thinking you're very confused. Put a 10 if you're thinking this is super, super easy. Let's see what the chat says. Scary. -100. Okay. 5 marks out the window. No, no chance. This is 5 marks. Still don't like it. Yeah, it's a bit of a weird one. Yeah? Okay. Right. Now, let's look at it together. I'm going to put this here just so we can read it and everything. Okay. So putting this here. Whoops. All right. So at the start of the exams, she puts 4 new batteries in. And she's used a calculator for 16 hours, but has another 4 hours of exams to sit. We need to find probably that her calculator will not stop working. So do we agree with me, guys, right? For her calculator to not stop working, it means that all 4 batteries, right, must last the entirety of 20 hours, right? Because remember, she's used it for 16 hours so far, and she's got 4 more hours to exit, 4 more hours of exams to sit. Yeah. So we need all 4 batteries to last for all four batteries, right, needs to last for 20 hours. Yeah. Okay. That's the first thing. Yeah. Now, it says that she has used her calculator for 16 hours, but has another 4 hours of exams to sit. So we're at the 16-hour mark, right? And we need it to last for 20 more hours, right? So this here is a conditional probability, isn't it? Because right now it's saying that she's at the 16-hour mark. She's got 4 more hours of exams to sit. Yeah. And we need a probability that a calculator will not stop working for the remaining of Alice's exam, which is 20 hours long, right? So what we're actually doing, right, is we're looking for the probability that her calculator lasts for 20 hours, right? Given that it has lasted for 16 hours so far. Does that make sense? This is the most important part of this question. Is that clear? Yeah? Good stuff. Yeah? Okay. Now remember, what we're doing here though, this is for 1 battery. So we're gonna need to finish off at the end. Yeah. So just remember, this is for 1 battery. Now, remember the independence, sorry, not the independence, the conditional probability formula, right? Now, what I always do with this one here is I'm gonna draw a normal distribution curve like this. Yeah. So we've got this here. Now, we've got the mean was 18. Yeah. And we know that we're looking for the probability of it lasting 20 hours, right? Which is this here. This part here, right? And given that it lasted for 16 hours. So let me put this 16 here. This is 16 here. So remember the probability, the conditional probability formula, right? Probability of A given that B happens is equal to the intersection of those ones, A and B, divided by the probability of B. Yeah? All right. So in this case then, well, the probability of you lasted more than 16 hours, right? This has to be, let me compare it. So we put this here. Probability of lasting more than 20, given that you last 16, right? Well, on the denominator, for sure, it will be the probability of you lasting 16 hours, right? And then, well, I need the intersection of you lasting more than 20 hours, right? And you lasting 16 hours, right? Well, remember, 16 hours is just here, right? Here and all the way, like this. Yeah, I'm going to wrap this up because it's going to get rid of the blue, but you guys get the idea, yeah? This is just all the way up to the end, yeah? 16 and over. But can we see from the diagram though, right? The intersection of both of these, right, is just this part here. So for sure, I'm going to have this here. Does that make sense? Because remember, it's that part of the entirety. So it's less than, or it's more than 16. And we're looking for a probability of it lasting 20 hours, right? If you look at the diagram, the blue part is the probability that will go on the top. Does that make sense, guys? Yeah, I would recommend drawing the diagram. For me, when I'm doing these type of questions, I would always visualize it. Me, I can't see anything, right? I wear contact lenses. I'm wearing contact lenses right now. I can't see anything. I'm blind as a bat, yeah? When I'm doing questions, I need to see what's going on here, yeah? Don't trust that on the roads. Trust me, for sure, for sure. For sure. It's so funny. I've had my driving license for 5 years and I haven't driven a car once. But yeah, cool. So let's calculate these now. Well, that's fine then. So let's work this out. Probability of L being greater than 20. Yeah, so let's do this quickly. So how do I go, guys? How do I go back? Oh, no, I press equals, don't I? Yeah, perfect. I always forget that. Probability of 20 is going to be our lower bound now, right? It's going to be the exact same thing. So it's going to be this value here. Yeah. That is the probability of being larger than lasting longer than 20 hours, isn't it? Yeah. So I'm going to put this here. And I'm just going to write this here. What is that? That's what I'm going to do. I'm just going to screenshot it. Yeah. That's this one here. Yeah. Okay. So I've got this one here. Yeah. All right. That's fine. And then the probability of me lasting more than 16 hours, is that not what we calculated in part A? It is. Yeah. But in an exam, I wouldn't even use that one. I would just go back and get the entirety of the numbers. Yeah. So I'm going to put 16 here. I get this here. Yeah. So I'm going to put this here. Paste this. Okay. So that means our answer is equal to that number on the top divided by this number on the bottom. So all I'm going to do now is just plug this in. So remember, when I go back to the normal calculator mode, this answer is going to be saved. Yeah. So I'm going to just go to menu 1 and let's just double check it's saved. It is, right? So I'm just going to do the top. Now for me, I can't lie, in an exam, I'm going to write out every single digit. Yeah. 0.308, 53, 308, 53, 75383, 75383. And I'm going to divide this by the answer. This gives me this here. 0 point. I'm gonna paste this too. Yeah. Now, we happy with this, guys? Part B done. Can we go on to the next question? Yes or no? Right. Not quite. Exactly. Yeah. Alex, exactly. So remember, what you want to do is remember this was the probability of one of the batteries lasting for 20 hours, given that it's lasted for 16 hours already. Remember, there are 4 batteries in Alice's calculator. So what do we need to do? Remember, we're going to say, well, probability of 4 batteries, yeah, lasting would be equal to this thing here, right? To the power of 4, isn't it? Because there's 4 of them. Yeah, we don't times by 4, we do it to the power of 4. So let me put this, so I don't need to cut it. Let me copy it. Yeah, like this. Like this. Yeah. So that will be our answer for part B. So let me put this into the calculator. This will give us an answer to the power of 4. This gives us that there. Yeah, 0.0396 to 3 significant figures. So I'm going to paste it and put it here. Yeah. So this is our answer here. Like this here. And then to 3SF, this is just going to be 0.0396. Does that make sense, guys? And that's 5 marks in the bag. We all okay with that? Why do each have to last 20 hours though? Because remember, the start of let's read it again. Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. Yeah. Find the probability that will last longer than 16 hours. And it says, remember, at the start, right? She's done 16 hours, right? She has another 4 hours of exams to sit. So her entirety of her exam are last 20 hours long. That's why it needs to last 20 hours. Is that okay? Yeah. Good stuff. Good stuff. Now, just quickly, let me just see again quickly. Why is it just the probability of lasting 20 hours on the numerator and not the product of lasting 20 and 16? So remember, well, first thing to just remember, it's not the product that would be on the top, right? It's the intersection, right, from the formula. Now, the intersection, though, if you look at the diagram, the intersection of lasting 20 hours and lasting 16 hours, right? Remember, we've got this here, don't we? Just do it one more time. This is lasting 16 hours, right? Here, all the way. Yeah. Now, where's the probability of me lasting 20 hours, right? It's here, isn't it? This is 20 hours, 20 hours. Now, where is the intersection of this one here? It's just this part. It's just the 20-hour part. That's why it's only the probability of you lasting 20 hours on the numerator. Is that clear? Does that make sense? Yeah. This was from the 2018 paper. Yeah. All right. So let's continue. We've got a couple more. All right. So got this here. It says Alice only has 2 new batteries, right? So after the first 16 hours of her exams, although her calculator is still working, she randomly selects 2 of the batteries from her calculator and replaces these with 2 new batteries, right? For part C, it says show that the probability that a calculator will not stop working for the remainder of her exams is 0.199 to 3 significant figures. Okay, so think about it. We've got 2 new batteries that she's got. So after the first 16 hours of exams, right? Her calculator is still working. She's going to take 2 of her old batteries, right? Because all of them are going to be old when you get to 16 hours. And she's going to fit them in with 2 new ones, right? We need to show the probability that her calculator will not stop working for the remainder of her exams is 0.199. Yeah. So what I would do here is I'll say I've got 4 batteries here. I've got 4 batteries. Yeah. All right. Now remember, if she takes 2 out, right, and she puts 2 in, those are going to be new. So I'm going to say, well, I've got 2 new batteries, right? And I've got 2 old batteries. Yeah. Okay. Now let's look at it here. She's taken 2 out after 16 hours. Yeah. Her exams last 20 hours long. So for the 2 new batteries, guys, can somebody tell me how long do they need to last for? What would be the probability I'm looking for? Exactly. So for the thank you very much, Leah. Afia. We're just gonna do 4 hours, aren't we? Yeah. So it's gonna be the probability of you lasting 4 hours, right? Right. Now remember, there's 2 of them though. There's 2 new batteries. So what we're gonna do is we're gonna square this, aren't we? Yeah. We're gonna square this, and then we've got 2 old batteries. Now remember, we are still at the 16-hour mark, right? After the first 16 hours of her exams, although her calculator is still working, she randomly selects 2. So we're still at the 16-hour mark. So we still need that conditional probability. So I'm going to put this here, put this in a bracket here, and it will be the probability of you lasting for 20 hours, given that you've lasted for 16. Yeah. And this is going to be squared too. Yeah. Because there's 2 old batteries. Remember, there's 4 in total. 2 of them are new. We only need 2 of them to last for 4 more hours because we've got 4 more hours to go. And we still need the two old batteries to last for 20 hours, given that it's lasted for 16 already. Yeah. And then obviously we know that in probability and is just times. Yeah. Does that make sense, guys? Is this clear? Yeah. Why did we put to the power of 4? Because for the other one, it was for all 4 batteries. Yeah. But can you see power of 2, yeah, to the power of 2, this is still 4 altogether. Yeah. So we're going to work out these now. Yeah. Well, the probability of you lasting 4 hours, that's fine. We can just do that very quickly on our calculator. Let me get that here. Click equals. No, I'm going to go back to stat. Normal CD. The lower bound is going to be 4. The upper bound is going to be 10 to the power of 10 because it's greater than 4. And then the standard deviation was 4, wasn't it? And the mean was 18, wasn't it? Yeah. So therefore we get this here. So putting this in here, I'm going to copy this here. So it's just going to be this one. This. Yeah. So the answer is going to be this, isn't it? It's going to be the square of this multiplied by the probability of you lasting for 20 hours, given that you've lasted for 16 already, which we just calculated in part C. Yeah. So what was it? What did we get for it? We got this one here, didn't we? Yeah. Now be careful though, because this was for 4 hours. This is for 4 batteries. So it's actually this one I'm using, isn't it? This one here. This value here, because this was the answer. Yeah. So I'm going to square this one like this. So we get that. So this is our answer, whatever this is equal to. Yeah. So let's put this in. So remember, we've got this stored in our calculator. Yeah. We've got this stored in our calculator. So I'm going to go back to normal. Now, let me just double check it's stored. Yeah, it is. That's fine. So it's going to be answer squared multiplied by that number there, 0.44621,621,0106 squared. Yeah. This gives us 0.199 to 3 significant figures, which is exactly what they wanted, isn't it? Can you see? To 3 significant figures. Does that make sense, guys? Yeah, we all okay with this? Yeah, good stuff. Good stuff. All right, cool. So now, let's do the last one here. Yeah. For 5 marks. For 5 marks. So here we go. I'll give you guys a chance to just read it, and you guys let me know what you think. Yeah. After her exams, Alice believed that the lifetime of the batteries was more than 18 hours. She took a random sample of 20 of these batteries and found that their mean lifetime was 19.2 hours. Stating your hypothesis clearly, using the factors of significance, test Alice's belief. So put a 0 in the chat if you're thinking normal distribution hypothesis testing, hate it, and put a 10 if this is just super, super easy. What are our thoughts? Let me just see the chat. 10, 8, 5, 9, 10. Good stuff. Yeah, I can see. Looks like it's okay. All right. So what I'm going to do just quickly, though, I'm just going to get something from another page, right? Now, when you're doing these hypothesis test questions, right, all you want to do is just remember the different types of, for example, this is a normal distribution hypothesis test, and we're doing it for the mean, right? So remember this from the book here. It says for a random sample size of n, right, taken from a random variable, the sample mean is normally distributed with mu, but sigma squared divided by the sample size, yeah? So what we're going to do here, remember, this is the lifetime, so I'm going to put L instead of X. This is normally distributed at this here, right? L hat, because we're estimating the mean. Mu, remember, was 18, yeah? And then remember, sigma, the standard deviation was 4, wasn't it, right? And we can see that n is equal to 20. So therefore, this would just be 4 squared divided by 20. Yeah, there. Does that make sense so far, guys? Yeah? Why is it normal and not binomial? It's a normal distribution, first thing first, because we're dealing with the mean lifetime, right? That's the first thing. And now remember, I can see why you're saying it may be not binomial due to the fact that that the sample, we have a sample size of 20 here. But remember with the sample, with the binomial distribution models, right? the probability of success or failure is fixed, right? What we're dealing with here is just the mean hours of lifetime. We've got a standard deviation here. So just use context clues when you're doing these questions, right? Question 5, we've got mean, we've got standard deviation, it's normal distribution here. Yeah? Okay. So let's just finish this one off. All right. So we've got this one here. Now, what do we have here? We've got this here. We've got she took a random sample of 20 of these batteries and found that their mean lifetime was 19.2. Yeah. So this is our observed value. Our observed value, right, is equal to 19.2. Yeah. Let me just make sure. Okay. So now, what you want to do, you can do this a couple of ways, right? I think probably the most straightforward way would just be to standardize, right? And look for the critical region. So again, always try and visualize what's going on here. Yeah. So we're looking for the probability of L, right, being greater than 19.2. Yeah. So let me just there's a lot of stuff I've actually missed out, to be fair. We've got this is a hypothesis test, right? So what do we have here? We've got the mu is equal to 18. And then so our null hypothesis is mu is equal to 18, right? And the alternative, Alice's claim that it's more than 18. Yeah. So it's what type of test is this, guys, as well? Just quickly. Exactly. It's a one-tailed test, right? Because what does it say? It says Alice believed that the lifetime batteries was more than, right? She didn't say it was different or not equal to 18. It says more than. So it's a one-tailed test for sure. Yeah. One-tailed test for sure. So we're just looking for one side. Yeah. All right. So what you want to do is you can just put this in here, to be honest, and see what you get. But what I would do, I think the most common way that we do is standardize it, to be fair. So I'll do that. Yeah. So remember, with our standardized distribution, right? It's normally distributed with standard deviation, mean 0, standard deviation 1. Yeah. So what you want to do is, in our case, right, we need to figure out our Z value. Yeah. Which is X minus mu, right, over sigma. Is that correct, guys? Yes or no? Is that correct? No. Remember, this is a sample. So it's sigma over root n. Remember, because we're dealing with a sample now. Be very, very careful. Yeah, we're dealing with a sample. Bro, setting us up. I'm just checking you guys are listening. I can see you guys having conversations in the chat. I'm just making sure. That's my job, no? Okay, so yeah, let's have a look now. So what is our observed value? Our observed value is 19.2. So we're going to say Z is equal to 19.2, right? Minus our mean, which is 18, divided by the standard deviation, right? So let's just do this here actually, just quickly. It's going to be, I'll do it in sigma over root n, right? Sigma is 4, n is 20, so it's root 20, yeah? So we got this here. So 4 over root 20, yeah? So that will give us the corresponding Z value that we're looking for. Yeah, now remember that, what was it again? It was a 5% level of significance, wasn't it? So what we're looking for is we're looking for the Z value of a 5% level of significance, right? So this area here is going to be 0.05, right? Remember, I'm looking on this side because it's greater than, yeah? This is going to be 0.05. We need to figure out what this Z value is for this one and compare it to the Z value of this one. Now, if the Z value of this one is inside this blue region, then we reject the null hypothesis, don't we? Yeah, and accept the alternative. If it's on the outside, we do the opposite. We accept the null hypothesis. Yeah, and we reject the claim. Yeah, so let's put this in our calculator and see what we get. Yeah, that's the first thing. So we put this here. So we've got this here. We've got 19.2 minus 18, right? Divided by 4 over root 20. Yeah. This gives us 3 root 5 over 5 or 1.341, blah, blah, blah. Yeah. So we've got, that's our Z value here. Z value is equal to 1.3412. Yeah. 1.341, sorry, 1.3416. 1.3416. Yeah. So that's our Z value, right? Now, what we want to do, remember, this is our Z distribution. Yeah. The mean is 0 here. Now, what we want to do is figure out what is this critical value, because this is our 5% level of significance, isn't it? Now, how do we get this? Well, you can just go on your calculator, right? And just figure out what that value is. And we can do this by using the inverse normal function. Yeah, where is it? Number 3. Yeah, so remember what this gives you. This inverse normal, you plug in an area, right? You plug in an area and it gives you the corresponding Z value, doesn't it? Or value on your distribution. Yeah. So in this case, obviously, we've got this already given to us. It's already default to the Z distribution. What area are we looking for? This is this is just the last 0.05. So all I'm going to do here is I'm just going to put in 0.95 on here. Yeah. And this gives me 1.644, doesn't it? Yeah. This gives me 1.644. So this Z value here is 1.644. Right? Let me just double check. 6449. Yeah. Let me just check the chat as well, just so we're all okay. Yeah. All right. Yeah. Now we've got this as our Z value. This gives us an area, right, of 1.34. Sorry, gives us an area of 0.05, doesn't it? Yeah. So now to finish off, we compare the value that we found, don't we? Which is this one here. Yeah. So all we're going to do now is we're just going to say, well, for example, that this 1.3416, right? Yeah. It lies inside, doesn't it? Yeah. Because it's more than, isn't it? Yeah. Oh, sorry. What am I talking about? What am I talking about? It's closer. Sorry. Thinking of something else. Let me just go back here. So let me do that again. 1 sec. So that should be on this side, isn't it? Because it's closer to 0. Yeah. Duh. Yeah. This one here is 1.3416. Yeah. So it's on the outside. So can we see, guys? It's not 1.3416 does not lie in our critical region. Does that make sense, guys? Yeah? Does that make sense? Yeah? Let me just see the chat. Yeah? So what does that mean then? Well, that means, just to finish off, really. So, okay, so let me just, where did I get 1.6? Okay, I've got 1.6. Let me just, you don't have to standardize, by the way. You don't have to standardize. I checked the mark scheme and that was the most common way of doing it. You don't have to standardize. But basically, let me just do it one more time because I think I kind of confused you guys. Let me do it one more time, yeah? So remember when you're dealing with hypothesis testing, you're just comparing your critical region, yeah? Now, this, because it was 0.05, right? The area, the significance level was 0.05, right? I need to find the critical value that gives us this, right? Right? Now, when I use the standard normal, the inverse normal, this gave me a value of 1.6449, yeah? So let me just get my calculator here again quickly. This here. This gave me this, yeah? I'll go back. If I click equals, remember 0.95, because that's just the last 0.05. This gives me a value of 1.6449, yeah? Now, this area here is 0.05, isn't it? Now, remember, we were observing this value here, 19.2. We standardized, right? And we said, well, our Z value, our corresponding Z value was equal to 1.3416, right? This 1.3416 lies somewhere here, doesn't it? Yeah? Right? Because it's smaller than 1.6, isn't it? 1.3416, right? 1.3416. So this lies outside of the critical region. Does that make sense, guys? Make a bit more sense now? Yeah? Okay, cool. So now what does it mean when it lies outside the critical region? Well, it means that you do not accept the alternative, right? You accept H naught. Yeah? Now you just contextualize it. Now, what was Alice's claim? Yeah? After exams, she believed that the lifetime of batteries was more than 18. Yeah? So all you would say now is that I'm just going to type it here. As Z value does not lie inside critical region, there is not enough evidence to support Alice's claim. And that's it. Does that make sense, guys? Yeah. What value would you get if we didn't standardize? So basically what I've done is I've found a critical region, right? What you could have done as well, you could have just done this as well. You could have just done, for example, you're looking for the probability of you observing that value. So L is greater than 19.2, yeah? And then you work this out and you compare this with your significance level. So let's just do that very quickly because it doesn't take too long. So let's go back here. Normal 7 CD. Now we're looking for 19.2 because this was the value observed. 19.2 and then 10 to the power of 10, right, is our upper. And then this is equal to the standard deviation was, remember, we're dealing with a sample now, aren't we? We're dealing with a sample. So it's going to be sigma over root n. So 4 divided by the square root of 20, yeah? Huh? And the mean is 18, yeah? We get this value here, yeah? This value is 0.08, isn't it? Which is more than, can you see? This is more than our significance level. So it's the exact same thing, yeah? Let me paste this here. Let me paste it. Yeah. This value, remember, our significance level was 0.05. This is more than 0.05. So therefore, we do not, what was it? We do not accept H1, yeah? Because remember, if it was less than, right? Because remember, look at this, look at the diagram. 0.08 corresponds to that, doesn't it? Because it's more than 0.05. It's more than the blue area. Does that make sense? So you could have done it either way. Yeah? Okay. Cool. Cool. Guys, again, sorry about overrunning. Just a quick one. Because I know we're not gonna go through it. I'm gonna put this in the OneNote here. But I had this large data set question here. Now, I know this comes up. It's not that many marks, but what I would recommend is between now and Tuesday is just to just have a brief look at the large data set. I've actually got a document I'm going to send you guys. So let me just, I found this online. Where is it? I found this online, right? Right. So what I would maybe do if I was you guys is just have a brief check of this. What I'm going to do is I'm going to put this in the chat. So 1 second. How do I do this? Cancel. All right. Your file, that's from your college data set, this here. It cannot be sent because it's currently enclosed. Okay, what I'm going to do, let me put this here 1 second. That's from your college. Okay. I found it online, so maybe, yeah. But let me just get this up. I need to close it apparently. Let me just close this and put this here for you guys. And then I should put it in, that should work. So I've got a couple of your computer data set. Okay, if you guys check the chat now, I've just sent the data set. I'll probably put in the link in the description on YouTube as well. And I also found this as well. So I think it's the actual data set. So let me just show you what I've just put there. Let me just share my screen with you guys just very quickly. What am I looking for? I'm looking for my browser. Yeah. So basically, let me open the Excel spreadsheet again. Or let me open the PDF I was looking for here. So yeah, I found this online, right? It's about 8 pages. Maybe just have a look at this and just get an overall understanding of the large data set. So just think about the different units of measurement as well for like daily mean temperature, total rainfall, all of this stuff. It summarizes it quite well. I've put this in the chat, and yeah, you guys should be fine. Make flashcards, memorize the whole tables. But yeah, how you guys all feeling? Obviously, as my students know, stats is my favorite subject. It's not, I don't like stats to be fair. But how did we find it? Is that all okay? I ain't reading all of that. Yeah. Cool. Guys, honestly, it's been an absolute pleasure teaching you guys. Honestly, it's actually been so much fun. I've got to say this, like, this was the first time I did a pure class. The first group I did a couple of weeks ago. That was the first time we doing a group. And I was proper nervous. I was like, oh, I do GCSE groups, they're easy, but A-level maths is hard. So I was asking my students, should I do it? They're like, trust me, you're a good teacher, do it. And then, yeah, I did it. And I put on YouTube, and then you guys have been so supportive. So I really, really appreciate it. And let me just see the chat. Got all recommendations. Now you're welcome, and you guys are all welcome. And it's so sad as well, because a couple of my students that I've been teaching as well, they're in the class. I've had my last lesson with a couple of them. A couple of my other students I had been teaching since year 9, and they're doing the A-level maths. They're doing the last exam on Tuesday. So yeah, but guys, how are we all feeling? Is paper 3 your last exam? Yeah. Last lesson tomorrow. Who said that? Who said that? Was that Lucy? Yeah, I know. It's so sad. So sad. So sad. Peak for Kev. Okay, 2 further maths. You know, further maths. I actually tutored that for a year. That was hard work. I don't think I'll be doing that. I would be doing groups for further maths, unfortunately. But yeah, but cool, guys. What you guys? What are you guys doing in uni as well? Let's see. Physics, computing, engineering, accounting. I can't see no maths degrees now. No maths. Medicine, sport, environmental science. Cool, cool, cool. Medicine. Okay, someone's doing maths. Maths degrees is crazy. Trust me, do you know what it is? At maths at uni, if you do further maths, then you don't even do any, you don't even learn anything new. Because when I started teaching further maths, I was looking at all of the work, I was like, this is what I did in uni. But yeah, but guys, oh yeah, thank you very much. Quick plug. So let me just go back because this is going to be on YouTube. So let me just go back. Where is it? So remember, if you're watching this on YouTube, guys, remember my YouTube channel is here. So we're on 942 subscribers, guys. Make sure you like, comment, subscribe. I'm also on TikTok as well. If you want to follow me here, I'm also on Instagram here. Is it going to load? Also on Instagram, also on Twitter. So guys, I want you guys to let me know how it all goes. Yeah. Please keep in contact. Honestly, it's been an absolute pleasure teaching you guys. Have a lovely, lovely summer. So this lesson is like my last lesson that requires brain power. So after today, I'm gonna book some holidays and I'm just gonna chill out. Yeah. So guys, it's been an absolute pleasure. I hope you guys enjoy your summer too. Do you think large essay is essential? Not really, but I would definitely look over it. It's only a couple of marks in the exam. Yeah. But guys, it's been an absolute pleasure. Enjoy yourselves. Good luck for the rest of your exams if it's applied. If not, good luck. But yeah, guys, been an absolute pleasure. I'm signing out. Enjoy yourselves. Take care.